Hello, everyone. I'm sorry I can't be joining you today in person, but I will be joining online to have your feedback and answer your questions about this presentation. The title of our paper is Enabling Downstream Machine Learning over the Textual Information Contained in Building Knowledge Graphs, written by myself, Mehrzad Shahin-Moghadam, PhD candidate at ETS University, Dr. Motamedi, my research supervisor, and Dr. Soltani, principal machine learning scientist at Procore Canada. Our work positions itself within the area of machine learning from the semantic models of the building information. So first, please let me set the stage by giving some background information about knowledge graphs and their relationships with the field of machine learning. So what is a knowledge graph? If we look at the current literature, it is hard to find a widely accepted formal definition of knowledge graphs. But in a general sense, a knowledge graph can be defined as a graph structure whose nodes represent real-world entities and the edges of this graph or network represent the interrelationships between these real-world entities. So to put it into perspective, let's assume a particular room inside a building as our entity of interest. Then we can start describing this entity by establishing its relationships with other entities inside the building. For example, we can mention other spatial or structural elements that have associations with this room. Or we can describe its shape representation in terms of geometry or even the current room temperature. And we can expand our graph by keep describing facts about all relevant entities, and the end result will be a rich semantic model of our building. And to do so, we can take advantage of the currently available information models such as IFC or rich ontologies such as break schema. With this introduction, we are now ready to define our research problem. Given the challenges of including geometry and time series data using the technologies that are available today to build a knowledge graph, technologies such as RDF, a knowledge graph that can be practically built to represent facts about our buildings today will mostly consist of textual information rather than numerical data. But this is why to take advantage of the conventional machine learning methods, we need low dimensional and dense vector representations. So with the absence of numeric data, the key question that remains to be answered is that how we can transform the textual and contextual descriptions inside the building knowledge graph into low dimensional dense vectors that can be used later as input to our machine learning tasks. To answer this question, we conducted this study to investigate the potential of knowledge graph embedding techniques. The main steps that we took in this study are depicted here on the right side. Here I focus on the embedding learning step. So to put it into simple words, a knowledge graph embedding technique takes all the nodes and relationships of a graph as the input and gives us back unique numerical vectors for each graph element as the output of the algorithm. For our current study, we investigated the effectiveness of one of the state-of-the-art knowledge graph embedding algorithms called RDF2-WEC. So the key rationale behind this algorithm is to train a neural language model using the famous word-to-vec algorithm, which is still one of the most widely used models to generate word embeddings. To do a quick overview of how RDF2-vec works, as the first step, we need to convert our graph data into sequences of entities and relationships. To do so, One option is to perform random walks on our graph network. To give an example, we take any random path between a starting and ending node and just follow the links to build our sequences. Then these sequences, which each of which can be viewed as natural language sentences, are used to train a custom board-to-vec model, which finally generates vector representations for each of the entities that were included in our input sequences or sentences. For our experiments, we took two types of structural elements, namely beams and walls, to examine if we can have two distinct clusters of embeddings for each of these two classes. For the training process, we used an existing building information model as raw data. Both IFC and RDF versions of the used model are publicly accessible from an online repository maintained by Ghent University in Belgium. When performing the pre-processing of our data, we excluded type relationships for our target classes, which are beams and walls. And the reason for this was to test the algorithm's ability to understand the surrounding contextual descriptions for each of the wall and beam elements, even when the explicit fact about the type of the object was absent from the training data. And finally, to be able to evaluate the results, we use Testing algorithm, which is a powerful technique for creating intuitive visualizations of high dimensional data. In our experiments, we set the size of the embedding vectors to 100. So at the end of the training process, we could represent each wall and beam element with a 100 dimensional vector in the embedding space. Subsequent to the training step, to evaluate the results, which means to test whether nodes of one type were embedded close together in the feature space, we used the testing algorithm to learn 2D representations of the beam and wall embeddings. So here on the right side, we can see the final 2D representation of the generated embeddings. We can see that wall and beam elements are positioned in the upper and lower corners of the graph respectively. However, as we can see, we didn't end up with two perfect clusters of beam and wall classes. And for that, we came up with possible explanations. One explanation has to do with the size of our training data. In fact, in these experiments, we used only the data from one individual building, which had about 200 instances of beam and wall elements combined together. But we did this on purpose. And this was to test if our proposed approach is effective to deal with the small amounts of training data, because we know in practice it would be difficult to find big number of building models that follow the same naming conventions, and because this approach relies on textual information, different naming conventions can significantly lower the performance of the model. So this is one explanation, and you can find others and further discussion of our results in the paper. We think this direction of research is worthy of further investigations. And in response to this question, we would like to highlight some of the potential areas where this line of research can make direct contributions. One major application will be the semantic enrichment of building information models. To give a simple example, imagine we want to label the spaces in our BIM model. Recent research has shown that machine learning approaches have certain advantages over the rule-based mechanisms to do so. But however, the current practice of machine learning from building information models involves various manual steps. First, we need to manually extract the data from BIM models. Then we need domain expert judgment to interpret and transform data into a tabular format so we can use them for our machine learning models. But with the help of semantic embedding techniques, we can transform our graphs into dense vectors and have them ready for various downstream machine learning tasks. And because this can be done on an unsupervised basis, we can avoid the hassle of data annotation, which means we can save a lot of time and money. And to give another potential application, we can take advantage of these embeddings to answer natural language questions from our building graphs. And this can be done by jointly learning the embeddings of the natural language statements and knowledge graph entities, which will be of high value to essential downstream tasks such as named entity recognition or graph entity resolution. We demonstrated the potential of neural language models for unsupervised learning of building graph embeddings happening purely based on textual descriptions. Our results show that existing techniques can be applied to preserve the contextual information contained in building graphs and to represent these understood contexts in the form of low-dimensional vectors. And we also discussed how these vector representations can facilitate downstream machine learning from building information models to help to solve real-world problems in our field. Currently, we are experimenting with this approach to map natural language statements into corresponding facts contained in building graphs so we can assist non-technical users to perform natural language queries over complex building models. And final word, to ensure the reproducibility of our results and for the benefit of the community, we would be more than happy to share our code and data with you. So please do not hesitate to contact us. Our email addresses are given here, and you can also find them in the paper. Thanks a lot for your attention.